electronegativity. So let's do a little bit of review before we get into what electronegativity actually means. The outermost energy shell, what is that called? Valence. In ionic compounds, metals, what do they do with their electrons in an ionic compound? Transfer shares. They transfer their valence electrons to form what type of bond? Ionic. In a molecular compound, valence electrons are shared to form a covalent bond. This is kind of like, this is the definition of what happens in ionic bonds and in a covalent bond. Okay, so this is what happens when those types of bonds are formed. Today we're going to justify what defines an ionic bond and what defines a covalent bond. Okay, because in the past we've been saying metals and nonmetals together make a ionic bond, and nonmetals and nonmetals together make a covalent bond. So today we're going to change the definition. Our learning goals for this lesson is to describe electronegativity and its trend on the periodic table, determine electronegativity difference, determine if bonds will be ionic or covalent, draw dipoles, and determine relative bond strength. I'm going to start off by giving you the definition of electronegativity, and then you're going to do the scavenger hunt activity. So, electronegativity, which I will call EN for short, is the relative ability of an atom to attract valence electrons. Okay? So it's almost like the atoms are playing tug of war with the valence electrons. Who gets the electrons? Who gets to hold on to more of the electrons? That's all going to depend on the electronegativity number. This number here on our periodic table, this is our electronegativity number. Okay, so this is my EN. Oh, that's a horrible N. EN. So I'm going to give you about 5 minutes. You're going to go through your data booklet and you're going to do the scavenger hunt. There are 6 questions. I'm going to give you 5 minutes to answer those questions, and then we'll come back and share our answers. Let's see how you guys did. Between metals and non-metals, which group has a higher electronegativity? Non-metals. So remember when we were drawing ions, Lewis got diagrams of ions. Let's say, for example, we have fluorine. Looks like this. To turn it into an ion, what happens to fluorine? Does it gain or lose? It gains. It gains 1 electron. Okay? It attracts. Okay? In a metal, let's say we have sodium. What happens in sodium when it ionizes? It loses an electron to get a positive charge. So this also goes in theory with what we've already learned. Nonmetals will always gain to complete their valence. They are more likely to attract electrons to their atom. Metals are more likely to give electrons away. Therefore, metals have lower electronegativity and nonmetals have higher electronegativities. Okay? Remember, electronegativity is the ability to attract electrons. Okay, which compound on the periodic table has the highest electronegativity? Hold on, I should say element. Which element has the highest electronegativity? Fluorine. What is it? 4. Fluorine. Find an element with an electronegativity of 3.4. Oxygen. Between carbon and nitrogen, who would have a stronger pull on valence electrons? Nitrogen. Why? Because higher electronegativity. Okay? It all depends on its electronegativity. Okay. Working on the side here, up down the side, which way, up or down, does the electronegativities increase? Up or down? What about across? Do they increase towards the right or the left? To the right. Who has the highest electronegativity? Fluorine. So the general trend is the increase diagonally towards fluorine. All right, for the following, rank them from lowest electronegativity to the highest. Okay, I think francium is first, lithium, calcium, aluminum, gold, oh, iridium. What's next? Carbon, sulfur, selenium, iodine, oxygen, and fluorine. Okay, so this is based on its electronegativity number. Technically, yes, between these two, it would be okay if they were flipped around, but I would like us to get into the habit of listing the lighter to heavier, okay? So always go lighter to heavier when you are listing them in order. Electronegativity difference is taken between two atoms that are bonded together. Okay, so a couple things that I want you to know. Electronegativity difference is only taken between two atoms that are connected by a bond. Okay, you cannot take electronegativity difference of multiple atoms, two maximum. So, electronegativity difference, I would get into the habit of subtracting the big electronegativity difference from the small electronegativity difference. If you do happen to switch them, small minus big, that's okay. Just take the absolute value. Parentheses indicate that you need to take, that your answer should be positive. So if you get a negative answer in here, the parentheses says that you need to have an absolute value, which is positive. Okay? So note that the parentheses indicate the answer will always be positive. Okay, so let's say we have this compound, chlorine, bonded to fluorine, and we want to calculate the electronegativity difference. So the electronegativity in this triangle is another way of saying difference, is equal to, parentheses, electronegativity of big minus the electronegativity of small. Okay, so we plug those numbers in. Fluorine is our big, so that's 4.0 minus 3.2, which gives me an electronegativity difference of 0.8. Only one decimal, no units. Between these two atoms, who has a stronger pull on the electrons? Fluorine. Fluorine has a higher electronegativity, so it's pulling those electrons away from chlorine. Okay, try this one on your own, and then when you're ready, you can look up here for your answer. Okay, you should get an electronegativity difference of 0.3. Who has the stronger pull here? Bromine, good. All right, electronegativity difference in compounds. Electronegativity difference is taken between the central atom and the peripheral atoms. Peripheral just means surrounding the central atom, okay? Therefore, electronegativity difference will need to be calculated for every connection or bond between two atoms. So connection / bond between two atoms. Okay, so here we have a compound where carbon is attached to hydrogen, chlorine, bromine, and fluorine. Again, it doesn't matter how you distribute your peripheral atoms, as long as they're all there and nothing's overloaded, you will get your marks. Okay, so we need to look at each connection. So the first connection I'm going to take a look at is between carbon and hydrogen. So the electronegativity difference between carbon and hydrogen is equal to 2.6 minus 2.2, which gives me 0.4. Okay? You need to do this for every bond. Okay? If there are different types of things, you need to justify and calculate the electronegativity for each different connection that you see. Okay, so electronegativity difference between carbon and chlorine is going to be 3.2 minus 2.6. Which gives me 0.6. Okay, I want you to take a moment and find the electronegativity between carbon and bromine and carbon and fluorine. All right, so what did you guys get for the electronegativity difference between carbon and bromine? 0.4. What about carbon and fluorine? 1.4. Okay? So please do not do weird things like multiply these numbers together, add or total or subtract them. That is not the goal of this. You have to calculate electronegativity difference for every new type of bond there is. Okay, types of bonds. So a non-polar covalent bond. When I'm thinking of non-polar covalent substances, it's things like oils, things like fat, things like okay, things that do not mix with water. What's happening is, in a non-polar covalent bond, there is a equal sharing of electrons between the two nuclei, okay, between the two atoms. So if we're looking here at this example, carbon, which is attached to two sulfurs, we know that the electronegativity difference is equal to the big electronegativity difference minus the small electronegativity difference. So for carbon, what is the electronegativity difference? 2.6. What about sulfur? 2.6. So what does that give me? 0. When you have a very low electronegativity difference of near to 0, that's when the electrons are being shared equally. These atoms have the same amount of pull on the electrons. So therefore, they are sharing them equally. No, between these, none of them is pulling them towards themselves more because their electronegativities are the same. Does that make sense? Okay, pure covalent is another name for nonpolar covalent, okay? And they form between the same atoms, between atoms of the same element. So they get an electronegativity difference of 0 as well. The only difference is that they are bonded to themselves, okay? So oxygen is bonded to itself. Phosphorus, even though there's 4, it's bonded to itself. That again will give you an electronegativity difference of 0. So to recap, there are nonpolar covalent bonds where they are different types of atoms that have a very low electronegativity difference. Pure covalent bonds will have an electronegativity difference of 0, and they are the same type of elements connected together. Polar covalent bonds. Okay. Have you guys ever heard of like the North Pole, South Pole? Or on a magnet, there's a positive pole and a negative pole. Compounds have that too. Okay. So on polar covalent bonds, electrons are shared unequally. Okay. Because they're shared unequally, the compound is going to form a slightly positive and a slightly negative side, making a very weak magnet. If we look at fluorine and bromine connected together, we know that fluorine has a electronegativity of 4, and bromine has an electronegativity of 3. Okay, so in this tug of war between these two atoms, fluorine is going to pull those electrons closer to it, okay? So it doesn't want to share. It wants as many electrons close to it as possible. Because it's pulling the negativity towards itself, it gains a partially negative charge, represented by this symbol called delta. And bromine, since the electrons are moving away from it, it's going to get a partially positive charge. So polar bonds are indicated using the Greek letter delta. Okay, I don't remember if this is capital or lowercase, but it looks like this. Okay, simple movements of the wrist. Okay, so delta negative indicates that there is a partial negative charge. This indicates that electrons are being pulled towards the atom, and it has the larger electronegativity. Okay, so the atom that has the larger electronegativity is going to pull the electrons toward itself. Delta positive. Delta positive has a partially positive charge on that side, and it indicates that electrons are being pulled away from the atom. Okay, and it has a smaller electronegativity. Okay. Bond strength. So, the greater the electronegativity difference, okay, difference, not electronegativity. The greater the electronegativity difference, the stronger the bond is, okay? So the larger your electronegativity difference is, the stronger your bond is. Okay, so we're going to take a look at example. We're going to rank the following from strongest to weakest bond, okay? Whenever you are asked to rank bonds based on their strength, you need to automatically think, I have to calculate my electronegativity differences. Okay, so electronegativity difference of the first compound between Na and Cl is equal to chlorine, which is 3.2 minus 0.9, which gives me an electronegativity difference of, okay, you get an electronegativity difference of 2.3. Okay, 2.3. O2, what's the electronegativity difference of that? 0, because it's pure covalent. Next one, we have aluminum chloride. So the bond between aluminum and chlorine. That's 3.2. What is the 1.6? Gives me an electronegativity of 1.6. I want you to take a moment and find the electronegativity differences of the rest of the compounds, and then we'll come back together and rank. Okay, so here are the calculations for the following electronegativity differences. For phosphorus, oxygen 10, 1.2, carbon dioxide 0.8, and 3.0 for calcium fluoride. Now, out of these, which one is the strongest compound? Calcium fluoride, right. Why? All right, good. This is our strongest because highest electronegativity difference. Okay, so let's rank these. Okay, so here's our rank. We have calcium fluoride. What's next? Sodium chloride. Next. Aluminum chloride. Next. P4O10. Then what? Carbon dioxide. O2 and S8. Okay, you can switch those based on the definition. Any questions, concerns? Okay, to summarize, in an ionic bond, which is also considered polar, electrons are transferred. Okay, so what happens here is that the pull is so great, but the pull is so big that it just takes the electron from the metal. Okay, it just takes it. It's pulling so hard that it just takes it and makes it its own. This happens when your electronegativity difference is greater than 1.7. Okay, this is an approximation. The relative bond strength. Ionic bonds are some of the strongest bonds and hardest to break. Okay, ionic are very strong. Polar covalent, electrons are shared unequally. It's pulling, so one atom is pulling way more than the other atom. However, it's not enough for us to just take that atom and make it our own. There's still a little bit of ownership with the other atom. This happens between an electronegativity difference of 0.5 to 1.7. Please note these are things that you will need to memorize. Okay? Non-polar covalent. This is equal sharing. Okay? Sharing is caring. This is kindergarten. Everything's perfect in this world. Okay? So, 1 second. So shared equally. Okay, because they're sharing so equally, I would say that the relative electronegativity difference for this is smaller than 0.5. Because they are sharing equally, and they're not really pulling on each other, it's much easier to break this bond. So this is the weakest bond. And polar covalent is in between. Okay, and we will discuss this type of bond further in the unit. This is an electronegativity difference scale. So we have a minimum starting at 0 because we can't have an electronegativity of 0, all the way up to 4. Okay, so it maxes out at 4. Here's how it looks like on a scale. From 1.7 to 4.0, we form an ionic bond. Okay, an example being NaCl that has an electronegativity difference of 2.3. We're going to call this 0.5. Between 0.5 and 1.7, we form polar covalent bonds. Example, carbon dioxide, which has an electronegativity difference of 0.8. Lastly, anything under 0.5, roughly, we will call it a non-polar covalent bond. So an example of this, let's say we have tin connected to tellurium. Okay, let's say there was a bond made like that. It has an electronegativity difference of 0.1. Now, this is what I'm talking about. Tin is a metal. Okay? Tin is a metal and tellurium is a non-metal. Based on the old definition, we would call this an ionic bond. Okay? We no longer use that definition. Electronegativity difference is what justifies if a bond is ionic or if a bond is polar or non-polar covalent. Okay? We will no longer use the metal, non-metal definition. Okay? So even though tin and tellurium are a non-metal plus a metal, it is not ionic because its electronegativity difference is so low. A dipole moment shows the next direction of an electron distribution. The larger the dipole moment, the stronger pull on electrons, aka larger electronegativity difference. The larger the difference, the bigger the arrows are going to be that we draw. A dipole moment is only found in polar covalent bonds. We do not draw them for nonpolar. We do not draw them for ionic. We only draw in polar covalent bonds. So let's say, for example, we have hydrogen sulfide, which looks like this. Okay. Let's draw a structural diagram for this compound. So it's going to look like that. Sulfur is in the center. We have hydrogen and hydrogen. Okay? Now, just based on, actually, let's do our electronegativity difference first. So the EN difference is equal to the electronegativity of sulfur minus the electronegativity of hydrogen, which gives me an electronegativity of 0.4 between the bond of sulfur and hydrogen. So that's a pretty small arrow that I'm going to be drawing. Okay, I'm going to use a different color to show you the arrows. So which one out of hydrogen and sulfur, which one has a higher electronegativity? Sulfur. So my arrow is going to point towards sulfur because that's where the electrons are going. So I'm going to draw a tiny little arrow that's pointing towards sulfur. Okay? Same thing on the other side. You want the same size of arrow because the electronegativity difference between the bonds is the same. Okay, it's 1.4 on either side. Okay, it's a pretty small arrow because it's like 0.5. This hydrogen then becomes partially positive. Okay, the sulfur becomes partially negative. Do we see how the electrons are being unequally shared between these two? They're being pulled towards sulfur. Those electrons are being pulled towards sulfur. Ah, making these bonds polar. Okay? So this makes a very weak-like magnet. Okay? They're partially positive and there's a partially negative side. Versus in an ionic bond, you have a full negative charge versus a full positive charge. That makes a magnet much stronger and harder to break. Okay, let's draw a dipole moment for this. So draw a structural diagram. Okay, and then we're going to find the electronegativity difference. So the EN difference, oh, that's not how you spell EN. EN difference between carbon and hydrogen is equal to 2.6 minus 2.2, which gives me an electronegativity difference of 0.4. Same thing, we're going to do the electronegativity difference of carbon between phosphorus, which gives me an 2.6 minus 2.2, which also gives me a 0.4. Okay, so between hydrogen and carbon, who is more negative? Who's more negative? Carbon or hydrogen? Carbon. Okay, so the arrow is going towards carbon. Okay, same thing on this side between carbon and phosphorus. Who's more negative? Carbon. And the strength of the arrow is going to be the same because again it's 0.4. Carbon becomes partially negative. It's being greedy between both of those atoms. It's taking them from both. And our hydrogen and our phosphorus become partially positive. Okay. Sometimes you will be asked to draw a net dipole. Okay? A net dipole is basically us finding the general area that the electrons are moving towards. So in this compound, the general area that the electrons are moving towards is towards sulfur. So this is called a net dipole. It shows the net movement of the electrons. Now, on this one, we have a linear molecule where the arrows are pointing at each other at the same strength. Okay, so let's say this is pointing in the positive 0.4 direction, and this one here is pointing in the negative 0.4 direction. Because they're the same strength of the same magnitude, they will cancel each other out. So there is no net dipole because dipole moments cancel each other out. Each other out. So then we cannot draw a net dipole for this. They are coming together and canceling each other out. Therefore, there is no net dipole.